The main objective of the practice was that the student could understand the difference between the quenching process, because in the Jominy test the bottom part of the Jominy tube creates martensite, and the hardest part will be at the bottom. This way the student should be able to select the best materials, because this way the student could be able to design the best temperature treatment to obtain the properties that the material is able to obtain for the purpose that it will be used. The material we used was a Jominy tube test of carbon steel 1045.
In this practice, we use a Jominy test tube to prove our material, which was a 1045 steel. First thing we did was to cover it in copper sulfate to give properties to the material. Then we put it in the oven at 900 degrees to create austenite for 1 hour. Then we take it out and we use the milling machine to cut a piece of that material to make our tests. For our tests, we test in the Brino machine every 2 millimeters, about 32 tests to prove our hardenability.
We did about 32 tests until we reached the 50 millimeters in the piece. The team expected that the harder part of the piece was the one that was in more contact with the water, because there it cools down much faster. Also, the martensite that was created in the part that was direct with the water, in direct contact with the water. So now the phase martensite, as we've been told, it was the harder part.
Comparing the results we have on our practice with the theoretical chart of the Jominy curve for our steel, we can see they are almost the same, except for the very first portion of it. The microstructure of a metal says how hard it is. Again, the cooling rate present on that part when we did the experiment. The harder metals are the high carbon ones, but again, depending on how fast they are cooled, they will get even harder because of the grain size made with the fast cool rate.
The ITESM standard for the Jominy test is the 8255 and determines the hardenability of steel. The test consists in quenching one end of a cylinder of 1 diameter. The hardability is the depth of which a material is hardened after a heat treatment. The real critical diameter after being quenched obtains more than 50% of martensite. The ideal diameter is to 50% of martensite in a given medium, and the cooling rate is from cooling rate table. The cooling rate at that point is 5.6 Celsius per second, and the grain size is necessary because with bigger grain size of austenite increase the hardenability because the inoculation site of perlite and bayonet is reduced. After this practice, we know now what is the Jominy test is. You can measure the hardenability by doing the quenching faster in one side than the other with water. Then do the test for measure the hardenability, and we can see if you cool faster one side, if you obtain more hardenability than the other side. This is because you get faster into the martensite, and the other side, the end side with the lowest cool, you have more martensite.
So as a conclusion, now we can see that the part that is harder of the piece is the one that was in direct contact with the water at the moment that it was cooling down. This we saw it in class, it was a theoretical class, but now in practice we can see that it was really true.
In conclusion, for this practice, we learned the measurements of the ITESM Jominy test piece and the differences of quench.
Conclusion is that this practice, I liked it a lot because we can see very easily how the cooling rate on a metal changes its properties, in this case its hardness properties.
As a conclusion, I can say that I now really understand how the quenching process affects the properties of the material. It's about the hardness, because when the water comes out at the bottom part of the Jominy tube test, it's harder because of the martensite that it's created. This is created because of the time of cooling. The bottom part is cooled faster than the top of the Jominy test, so the martensite created at the bottom was faster than the top of the Jominy test tube.